In this lecture, we continue with our discussion on capacity, demand, time, formulation of component reliability. So far, we allowed the capacity and demand to vary non-randomly in time. Now, we are going to start with letting the loads occur according to random pulses, meaning pulses with random magnitudes. And then we will keep adding features to that. So let's start with C being time invariant, so the strength does not degrade with time, and the loads occur according to pulses, so there are nt of them, so Q1, Q2, Q3 all the way up to Qnt. So nt being the number of occurrences in the time in question, and we know what it is, so n is not at this point a random variable. Now we assume, it's a reasonable assumption and which helps with the computation and formulation, is that these loads form an IID sequence. So all the Q's are mutually independent and they have the same distribution. Let's call it FQ. We also make the assumption, and which again is very reasonable, is that the loads are independent of the capacity. So we have n plus 1 random variables at hand. The reliability function can be written in terms of these. So it's the probability that Q1 is less than C0 and Q2 is less than C0 and Q3 is less than C0 all the way up to Qn is less than C0. So all the loads must be less than the capacity for the structure to survive, and that the probability of that is our reliability. So that's the definition. Now, can we simplify this? Because this is an n-dimensional joint probability. So it's really difficult to handle. Even though the Q's are independent, and they are independent of C0 as well, but these events, these n events that you see on the equation on the right side of your screen, they are not independent because C0, a random variable, appears repeatedly in them. So we cannot simplify this as the product of the individual probabilities. However, there is a way out, and if we bring in the theorem of total probability, as we have done many times. So let us say we condition this reliability, which is nothing but a probability, on a particular value of C0. So let C0 take an arbitrary constant c, little c, and based on that conditioning event, we can express the reliability as P of Q1 less than C and Q2 less than C and Q3 less than C all the way up to Qn less than C. It's the same thing as you see in the top equation, but there is a significant difference, is that now C0 is not there. We have a non-random C. The little c is non-random. So as soon as that happens, we are free to take the product of the probabilities, because now the individual events Q1 less than C and so on, they become independent of each other. So we have the conditional reliability at time t, given that the capacity has assumed a particular value, little c, is the product of the individual probabilities that each load is less than that capacity. So that's quite helpful. And further, since each of these probabilities is nothing but the CDF of the load evaluated at C, so we have the next step as the CDF of Q, FQ evaluated at C raised to the power of n. So that is the conditional reliability of the component at T conditioned on a particular value of the strength. Now let's complete the application of the theorem of total probability, and we integrate out all values of c. So it is integration of the fq to the power of n with respect to the PDF of c0 and c taking all values. Here we have 0 to infinity. So this is the way that if we understand the underlying physics of the problem, the mechanics, that the reliability function can be evaluated in terms of the load distribution, the knowledge of the capacity distribution, and the number of loads that occur within or during the time interval 0 to t. So that's how t shows up as one of the parameters of the reliability function.